Now we will see the next problem in root-locus diagrams. The problem statement goes like this. Show that the root loci for a control system with open loop transfer function gh of s is equal to k into s plus 1 divided by s into s minus 1 is a circle with center at minus 1 comma 0 and radius root 2. So in this problem we need to show that whatever the root loci we get for this particular system is a circle, or the circle is a part of the root locus. So this problem, in this problem we have to show that we have a center and also radius, those values. Center is at minus 1 comma 0 and radius is root 2. There are two ways to solve this problem. One is analytically, other one is graphically. We will see how to solve this using analytical method. So in analytical method, let us take the open loop transfer function gh of s. We know that gh of s is equal to k into s plus 1 divided by s into s minus 1. And we know that s is equal to sigma plus j omega, which is a complex frequency. Let us substitute that s is equal to j omega in the given transfer function. So you will be getting gh of s where s is equal to sigma plus j omega is equal to k into, so I have a numerator s plus 1, therefore it becomes sigma plus j omega plus 1. In the denominator we have j omega sigma, so we have sigma plus j omega in place of s, and also we have s minus 1, therefore sigma plus j omega minus 1. So this is the gh of s where we substituting s is equal to sigma plus j omega. Let us write the phase angle expression for this particular gh of s where we are substituting sigma plus j omega in place of s. Then if you find that we know how to write the phase angle, tan inverse of imaginary part by real part. So angle of gh of s is equal to, so in numerator we have s plus 1, that is sigma plus j omega plus 1. So what will be the equivalent phase angle? Tan inverse of, we have sigma j omega, so omega divided by sigma plus 1. And the denominator we have s, that means sigma plus j omega. Since it is the denominator, then we will get the minus, therefore minus tan inverse omega by sigma. And of course the third one we have minus because of the denominator, and also we have tan inverse omega by sigma minus 1. So this is the phase angle equation of gh of s. Now what I need to do is equate this phase angle to 180 degrees. That means I am going to use the phase angle condition of the root locus. So phase angle condition is angle of gh of s is equal to 180 degrees plus or minus 180 degrees. Let us say I will take plus 180 degrees now. So when you equate this, let us see what you will get. We have the equation already. So tan inverse of omega by sigma plus 1 minus tan inverse omega by sigma minus tan inverse omega by sigma minus 1. So take the tan on both sides. So when you take the tan on left side, first two terms I am going to take tan, then third one again tan, and after the equation for 180 degrees I am going to use tan. So when you do that, this will be tan a minus b, so it will be a minus b divided by 1 plus ab, and again I have a tan of that, directly you will get, because tan of tan inverse something will be that something will come here, and tan 180 is, that is 0. So what will be the resultant? The resultant will be you will get omega by sigma plus 1 minus omega by sigma minus 1 over 1 plus omega by sigma plus 1 into omega by sigma minus 1. If I take that minus omega by sigma to other side, because the right side we have 0, so this minus becomes plus, you will be getting omega by sigma. So this can be simplified very easily. Then if you simplify this, you will get minus 2 in the numerator divided by sigma square minus 1 plus omega square is equal to, so we have 1 by sigma. So again if you simplify, you will be getting an equation like omega square plus sigma square minus 1, then we have plus 2 sigma is equal to 0. So let us add and subtract 2 here. so that you will be getting a standard form, because we are going to show that that whatever the root loci we get, that root loci is a form of circle. Then in the process, if you add 2 and subtract 2, then I can write this in this form, like we have omega square as it is plus sigma plus 1 whole square is equal to 2. Omega square plus sigma plus 1 whole square is equal to 2. Then still if you write in this form, I will take this first one, therefore I can write it as sigma plus 1 whole square plus omega minus 0 whole square is equal to root 2 whole square. So when I say root 2 whole square, that will be 2 only. So look at this equation. When you look at the equation of the circle, let us say equation of the circle is x minus h whole square plus y minus k whole square is equal to r square, where h and k are the center and r is the radius. When you compare these two, what will be the h? The h is going to be minus 1. And what is k? K is 0. Then what will be the center? Minus 1 comma 0. So the center of the root loci when it forms circle is minus 1 comma 0, plus what will be the r? When you equate the r, that is going to be root 2. So we can show that the given open loop transfer function will have a root loci, and the root loci will be in the form of circle, and that circle will have a center minus 1 comma 0 and its radius is root 2. So this way we can prove analytically how the root locus form a circle of the given open loop transfer function. Graphically also we can do that. So we know the steps to draw the root locus diagram, and the given open loop transfer function is gh of s k into s plus 1 by s into s minus 1. We know that step 1, there are steps to be followed, and the step 1 is locating poles and zeros. What are the poles here? There are 2 poles, s is equal to 0, s is equal to plus 1, 2 poles are there, p is equal to 2, and there is only 1 0, s is equal to minus 1 and z is 1. Now I have S plane here, so left of the S plane, right of the S plane. Then what are the poles? Poles is s is equal to 0 and another pole is s is equal to plus 1 in the right of the S plane. That means this open loop transfer function is unstable. We have one pole in the right half of the S plane. Now, so I have 0 at s is equal to minus 1. So left of the S plane at minus 1 I have 0. So there are only 3 components, 3 elements, 2 poles and 1 0. So this is the location of poles and zeros. Once you have poles and zeros in the second step, we need to identify the area of the root locus. We know how to identify the area of the root locus. Now if you look at take the entire real axis, then I can divide the real axis into different segments, and I'll start from plus infinity to plus 1 is one segment, plus 1 to 0 another segment, 0 to minus 1 to infinity. So this we have different segments, and each segment you may be having root locus or you may not having root locus. Let us see which one is having root locus. So when you take plus infinity to plus 1, if you take any point on that particular segment, and if you look at right side of that point, how many poles and zeros are available? So in this case no poles and zeros, which is like it is an even number. So whenever you have even number, that particular segment you don't have any root locus. Then next segment is from plus 1 to 0. Yes, if you right side count, then there is a one pole. It is an odd number, which means from 0 to plus 1, yes, we have root locus area. So you can just put hash lines, that will be the root locus area from plus 1 to 0. And 0 to minus 1, we don't have any root locus. Minus 1 to minus infinity, I will have root locus. So root locus can exist only on the real axis from plus 1 to 0, minus 1 to minus infinity. In the third step, we need to know what are the asymptotes, centroid and asymptotic angle. That means complete information of the asymptotes. We know the number of asymptotes. A is equal to P minus Z. So we have P is 2, Z is 1, so A is 1. That means you will have only one asymptote. If you have one asymptote, we know the angle, that is obviously minus 180 degrees.